Alright, so in this video I just want to talk briefly about quasi-extinction risk and expected minimum population size. These are two concepts that are interrelated, and we use them a lot when we're thinking about small populations that are vulnerable. The main problem we have with small populations is they're subject to high levels of demographic stochasticity. So what we have here is a population that's growing logistically. It has a carrying capacity of 100, so right up here somewhere, starting off with a population size around 30, and there's a fairly high level of stochasticity associated with random births and deaths. That's all that's going on here. There's no environmental variation, just the random births and deaths. So individual traces of populations are shown in light gray, and so the more of them there are in a particular area, the darker the color. And so early on, there's everything is pretty close to where we started. It is growing on average. But you can see there's some populations that do really badly and others that actually rise quite high, well above carrying capacity, and then start to wobble around. If we come out here to 50 years, there's actually a distribution of population sizes. And so what we often do with this kind of thing is we turn it into, at one particular time, say year 50, we're going to calculate what's called the cumulative frequency distribution. So the way to read this thing, put population size down on the x-axis and cumulative frequency on the y-axis. So the smallest value at that time is going to be down here, starting at 0.01, and the largest value is where this cumulative frequency curve hits 1. So at this point we've got 100% of the observations are less than this value. Down here, 100% of the observations have population sizes larger than this value. So we can say grab a population size like 80 and read up, and then whoops, wrong way, and then across. And what we can see is that there is about, say, 55% of our populations at year 50 have population sizes smaller than 80. What happens if we increase the birth rates by 10%? So now we get the population rises faster. It also has a higher carrying capacity. We end up with a greater distribution, or a distribution that's spread over a higher set of values. And so what has effectively happened by increasing the birth rate is we've shifted our extinction risk curve, cumulative population curve, over to the right. So now this red curve indicates what we get when we have a population that has a larger value of higher birth rate. One way we think about these cumulative frequency curves of population size at a particular time is called the quasi-extinction risk. So what we want to do, extinction is when the population hits 0, but our models might get, because they're ignoring genetics and other features as well, they might be getting a bit wobbly as we get down to very small population sizes. So often what people will do instead is they'll choose a particular value of population size, say 50, and instead of calculating the probability of getting to 0, they calculate the probability that the population is below 50. This is called quasi-extinction risk, and you can get it directly off of these curves. So 50 is about here, so the quasi-extinction risk for the population in the black line is about 0.2, whereas the quasi-extinction risk for the population in the red line, the quasi-extinction risk for 50 is 0. So to get a similar sort of quasi-extinction risk, you'd look up here as a probability of getting about below, say, 150 has about a 20% probability. So that's one way, using quasi-extinction risk, that we summarize this kind of population output when we have stochasticity giving us a distribution of population outcomes.